Hey class! Today I will be teaching you about asymptotic analysis and why you should care about it. This is a sequel to my previous video on big O notation, so if you're interested, you should check it out. If you haven't seen it though, no worries because we're going to do some review. Recall that when we analyze the asymptotic behavior of a function, we don't care about the behavior for small inputs. Because we care about how the program scales, we only care about the function behavior as the input size goes to infinity. Let's do a review of the formal definition of big O. A function f of n is in the set big O of g of n if there exists positive constants c and n naught, such that for all n greater than n naught, 0 is less than or equal to f of n is less than or equal to c times g of n. In this example, we can visually see that f of n is in big O of n. Now for some more review. Recall that because we were interested in asymptotic behavior, we can ignore constants, so for example, big O of an plus b is the same as big O of n. We can say that f of n is in big O of g of n if f is at most the order of g. And, for an example, 42 is in big O of 1, big O of log n, big O of n, and big O of n squared. Also remember that when describing asymptotic behavior, we like to choose the tightest bound. So for the example that we just gave, even though 42 is technically big O of n, it is more descriptive to say that it is big O of 1. You might be wondering, how else can we describe asymptotic behavior? That's a great question, and it's what we will discuss for the remainder of this video. Let's go back to our big O diagram. If we switch these two terms around and update our diagram, suddenly we get big omega. Formally, f of n is in big omega of g of n if there exist positive constants c and n naught, such that for all n greater than n naught, 0 is less than or equal to c times g of n is less than or equal to f of n. Informally, f of n is in big omega of g of n if f is at least the order of g. In this diagram, we can see that f of n is in big omega of n. Here are some examples. Now we can fill out this handy table with what we just learned. The symbols we use for asymptotic analysis have a parallel to arithmetic, which I've listed here to help you familiarize yourselves with asymptotic analysis. What else is there? That's a great question, Tim. Let's check it out. Formally, f of n is in little o of g of n if for all positive constants c, there exists a positive constant n naught such that for all n greater than n naught, 0 is less than or equal to f of n is less than c times g of n. Here I've only drawn a line for one such c because drawing all of them would take up the whole graph, but you can imagine how any parabolic function will satisfy these conditions. Informally, f of n is in little o of g of n if f is of lower order than g. This is different from big O because in big O, f and g can have the same order, but in little o they cannot. Note that the definition for little o is very similar to the definition for big O, but there exists becomes for all and less than or equal to becomes less than. Here's some examples. We can fill out our table with little o. Now let's move on to the next one. Formally, f of n is in little omega of g of n if for all positive constants c, there exists a positive constant n naught such that for all n greater than n naught, 0 is less than or equal to c times g of n is less than f of n. Again, I've only drawn a line for one such c, but you can imagine how any constant function will satisfy these conditions. Informally, f of n is in little omega of g of n if f is of higher order than g. This is different from big omega because in big omega, f and g can have the same order, but in little omega, they cannot. Similar to little o and big O, the definitions for little omega and big omega are very similar, except there exists becomes for all and less than or equal to becomes less than. Here are some examples. We actually cannot use little omega to analyze 42 because it is a constant which is the lowest order function. With that, we can fill out our table with little omega. Now let's do the last one, big theta. Formally, f of n is in big theta of g of n if there exist positive constants c1, c2, and n naught, such that for all n greater than n naught, c1 times g of n is less than or equal to f of n is less than or equal to c2 times g of n. So essentially, f of n is sandwiched between these two lines as we can see in the diagram. Informally, f of n is in big theta of g of n if f is the same order as g. Whereas there are many ways to correctly analyze functions using the other symbols, big theta has one correct analysis if we ignore constants. 42 is in big theta of 1, 3n squared plus 2n plus 1 is in big theta of n squared, and n factorial is in big theta of n factorial. Now we can complete our table. Now that we have the complete table, I want you all to notice a few things. I included the mathematical parallel because a lot of similar principles from these concepts in math also apply to asymptotic analysis. For example, if a number is equal to x or less than x, it follows that the number is also less than or equal to x. Similarly, if a function is in theta of g of n, or in little o of g of n, that function is also in big O of g of n. Another thing I want you to notice that can be a good memory trick for remembering which symbol means what, is that all of the capital letters allow F to be the same order as G, whereas the lowercase letters do not. Something else I want to quickly touch upon is that if the previous table did not work for you, it might help to think of these symbols in terms of limits. We can think of these symbols in terms of the limit of the ratio between f of n and g of n as n goes to infinity. And in English terms, we can think of the growth rates of f and g. So f of n is in little o of g of n if f grows slower than g, and the limit as n goes to infinity of f of n over g of n is 0. F of n is in big O of g of n if f grows no faster than g, and the limit as n goes to infinity of f of n over g of n is less than or equal to some positive constant c. F of n is in big theta of g of n if f grows at the same rate as g, and the limit as n goes to infinity of f of n over g of n is equal to some positive constant c. F of n is in big omega of g of n if f grows no slower than g, and the limit as n goes to infinity of f of n over g of n is greater than or equal to some positive constant c. And lastly, f of n is in little omega of g of n if f grows faster than g, and the limit as n goes to infinity of f of n over g of n is infinity. Okay, that was a lot of information, so let's get some practice. Now it's your turn. Can you describe the function n squared plus 5n log n plus 3n plus 1 in as many ways as you can? Feel free to pause the video to try this out for yourself. Here's what I came up with. There are just a few things I want to point out. First, since we are concerned with the asymptotic behavior, we only care about the largest term, which in this case is n squared. This is because as n goes to infinity, the n squared term is going to dominate, so we can ignore the smaller terms. Something else I wanted to point out is that every function I use for little o, I also use for big O, because little o is a subset of big O. Similarly, every function I used for little omega, I also used for big omega, because little omega is a subset of big omega. Lastly, the function for big theta can also be used in big O and big omega. So, why care about asymptotic analysis? Knowing all these tools for describing asymptotic behavior of functions gives us more precise language to describe how our programs scale. But, to be honest, practically people just use big O, even though big theta is more precise. I don't really know why, and I personally think we should use big theta more, but that's just the way it is. And people don't typically use the omegas because we're usually more interested in an upper bound in how a program scales rather than a lower bound. This table is a pretty good summary of what we learned. We learned about different ways of analyzing the asymptotic behavior of a function using little o, big theta, big omega, and little omega. One way to think about these is about the relative order of the functions, and we can draw an analogy to these mathematical symbols. Another way we can think about this is comparing the growth rates of the functions and the limit as n goes to infinity of the ratio between the two functions. Thank you so much for watching, and please, feel free to comment any topics you would like me to cover next, or any feedback for how I can improve my videos. As always, this is your CS Professor of Fun.